Okay, so this is the definition, and so let's take a moment to appreciate what new we're seeing here, and it is a big deal because it's probably one of the most abstract definitions that you have seen. So think about it. Even if you in calculus, it's everything is grounded in reality. So it is, at least in part, is what we're seeing there. And around us, the world, the real numbers and all that is somewhat realistic, and the motion and all of that. At least it's at the bottom of it. It is real, and this is entirely abstract, and that is the reason, by the way, why we prefer to use the word axioms rather than properties, because properties come later. You have a definition, and then you derive properties from the definition. Here we start with these properties, and then we derive everything else from it, with nothing else coming into play. So the examples that we considered later were just that, examples. So these are manifestations of this abstract idea that we have. So whatever we're going to prove about these will be applicable entirely to any of the examples that we have seen, and no matter what the variety of in nature that they are. Okay, so it may be calculus, maybe geometry, maybe so starting with numbers as we did, then geometry, and here calculus. Okay, so just a few examples of close relations that all satisfy these properties, and then whenever we see something like that, we will have a theorem for that. Also, one of the most abstract theorems that you can see in this class, especially, and then so that's the value and the challenge of this kind of axiomatic approach that is taken in the modern mathematics, rather than looking at the reality as a guidance. We actually going backwards, and we start with axioms, and then rely on axioms entirely. Axioms as few as possible, combined with logic, a little bit of sets, and then you can derive anything you want about these. Okay, so importance. So why is it important? One example that I don't have here is somewhat more profound. It is just explaining what a number is. So what is 5?
It's a whole number.
Well, you'd have to explain what numbers are. So the equivalence relation, you can use them to understand numbers rather than having numbers and then illustrate this idea with numbers. That's fine, which is what I did. But you can actually go way back and understand what a number is, and with this approach. In fact, it may have happened exactly that way. That's maybe how numbers were invented. That's how the story goes. I don't know if you've heard of it. So it's like thousands of years ago, there were no numbers, and there was this shepherd or farmer rather, and he had a herd of cows. Okay, and he would let them out in the morning from his corral. Okay, but he cannot count. Okay, so in a day we maybe had 100. I mean, we would say 100, but he didn't know. He didn't have any numbers. So then he doesn't know when they come back. He doesn't know if he got all of them. You see the problem, right? No numbers. So what do? Well, the story goes, he got a bunch of pebbles, and every time cow leaves the corral, he would set one aside, and then another aside, and then at the end of the day, when they walk in, once again he removes from that pile one pebble and throws it away. So if there are pebbles left, he knows that there are some cows that haven't come home. Okay, and then he will search for them. And if there are just a few of them, he knows even every time he found cow, once again brought it back, threw out the pebble, and he knows that he's not finished. Okay, so as you can see, it is a surprising thing. Then what does it have to do with equivalence relations? It is an equivalence relation between sets of of the same quantity. So 100 cows and 100 pebbles are equivalent. And that's how number 100 appears. Okay, so that started with that shepherd hypothetical, and then the next one was maybe some high priest, and he was counting stars. And once again, they didn't have any numbers, so he could put aside something or make a mark on somewhere in order to count them. And then making those marks, and those marks gradually turned into actual numbers and numbers, written numbers that you can do algebra with. It's quite possible that actually like high priest people did it one way, and then some kind of trade people, shepherds and all, they did it differently. But ultimately, at some point it has merged, and then very different sets, as long as they have the same number of elements, they then declare it equivalent. So how do we know that they have the same number of elements without having numbers? Well, that shepherd did it one by one. Cow, pebble. So if you create a correspondence, you might remember what they called one-to-one onto functions. Remember those? Okay, so that's what it is. So there's a bunch of pebbles here and a bunch of cows there, and you establish a one-to-one correspondence between them. So for each pebble, there's only one cow, and for each cow, there's only one pebble. So these are relations that it is another kind of equivalence relation. So once again, two sets are equivalent if they have the same number of elements. You don't need number there. It's not about numbers. That's how you get numbers. Establish relation between sets of the same size. Okay, and then 5. What is 5? Then 5 is the class of all sets with 5 elements. It blew my mind at some point in the past, so I brought it up. We'll look into that later. At this point, we'll stick to more mundane examples such as these. And in fact, I have another one that I thought of. So once again, something more mundane than just explain numbers from nothing. That is a big one. Let's take something simpler, but a different kind than these. So outside of mathematics, here's one. An equivalence relation is be a brother of is an equivalence relation. On the set of men. Okay, okay. Well, is it? So the biggest problem is, are you your own brother? That's the reflexivity property. Is the person equivalent to himself? And so the question probably not, but by any common sense, you probably won't call yourself your own brother. But the rest of the axioms are satisfied. So if he is my brother, I am his. Okay. On the other hand, if I am brother of that person and he is brother of his, we are also brothers. Okay. So the other two axioms are satisfied. So 1 maybe, 2 yes, and 3 yes. If you try to go with say cousins, you will have pretty much the same problem. Because once again, are you your own cousin? No. I would say no. Well, then you're not your own brother either. So, what?
I don't think you're your own brother.
Right. Well, the problem. Well, let me tweak it a bit. How about half brother? Well, there once again, our first axiom is clearly unsatisfied, but. The second is, so 1, well, yourself is probably not. Number 2 is satisfied. What about transitivity? Half brother of your half brother is your half brother?
So you're saying your half brother's half brother?
Yeah, is he your half
So
brother?
is it a quarter brother?
No, that's not how it works. Well, I guess we'll do in mathematics. So definition is in order. What makes two persons brothers? They have the same.
He's your half brother-in-law.
No, that doesn't count. No, brother is the person who shares your both parents. Both parents. Half brother, one.
Yeah, sometimes. Yeah.
So is it? Well, that be careful. Half brother is a person who shares one parent. There is some ambiguity in the statement.
So they could be, but they could also not be, because they could be with the same, like, say the mom is like the mother of all three of those kids.
Yeah.
They have different dads, but then like
They all have brothers. So no, that's fine. Now the problem here is that you have to be mathematically look at the statement. A person who shares one parent. You have to be precise here, and you have to say exactly one parent, because you share a parent with your brother, right? But you share two. So this one is like existence and uniqueness. You have a parent that you share, and there's only one. That makes you a half brother, because if you have two, you're not half brother, you're brother. Okay, so exactly one parent. You share exactly one parent. That makes you a half brother. Okay, so the third axiom, once again, the first axiom seems to be failing, but what about the third? Your example doesn't work. So same mother, they all have brothers.
it doesn't work.
No, I mean it seems to work. The axiom 3 works for your example. That's what I
Yeah,
mean.
but then it can also not work.
Well, that's my point. Is there an example when to show that this doesn't work? It might not.
Your half brother from your mom, if his dad has another kid with someone, then
Right. That's right. So, so no. Right. So it fails. So for brothers, the axiom 3 still is satisfied. For half brothers, it does not. So as you can see, with the example that we saw yesterday was failing equivalence relations was when the symmetry fails. So now we saw how the reflexivity might fail just because based on the definition, and then this is how the transitivity fails. Any kind of relations, they are frequently reversible, but sometimes they're not transitive. So anything, being brother, being sister, might not be transitive if you're making two steps. So, by the way, in the first example, equivalence relation on brothers is so it's a person who you share both parents with, and it's not yourself. Okay, because you share with yourself your parents, so, but you're still not your brother. Okay. Okay, so some of the examples, as you can see. Okay, so now the example that, however, still the standard example that have enough complexity as well as enough simplicity, and I'd say it is concrete enough and then unambiguous. That's the problem. But equivalence in real life, their ambiguity is and careful definitions are problematic. Even though probably if you're writing a will and you're saying half brother, that matters. And I am leaving everything to my half brother. Say it will matter. So if you have also brother, you know that you're not leaving to your brother. So the point is that the half brother is not a brother, and so the definition will matter. So in legal situations, this one congruency, no ambiguity, no problem of any kind, and we have a bunch of them right away. So once again, two numbers are congruent modulo n if they have the same remainder. We proved the three axioms to begin with: reflexivity, symmetry, and transitivity based on our remainder theorem. And the visualization, I still have, so nobody threw it out, how you form a circle So you have, suppose this is all your real numbers are here, integers are here. So if I just go ahead and start writing 1, 2, 3, 4, 5, 6, 7. Okay, so numbers, imagine that it goes infinitely in both directions. I realized when I was leaving that I should have brought what matters, what helps with the, it's like the tailors use, measuring tape. Yeah, measuring tape for, so for example, if you go around your waist and you have 30 inches waist, then when you make a full circle, then 30 align with 0. So that's what we're talking about. And if your tape hypothetically is infinite, then it will be wrapping around every 30 inches around your waist. But if we are dealing with integers only, so say will be divisible by 5, I align 5 and bring it, I forgot 0. That 0 is the most important one. So imagine that on the left is 0, so I'm bringing that 5 and align it 5 with 0. Okay? So align 5 with 0, and that creates this cyclic thing that everything turns into a circle with infinitely many loops around it. Okay? So that's the idea of the congruency, which reminds me that let me give you something that I could call an optional homework, but I hope you will think about it for a bit. So it is about congruency, but what if we combine two congruences together? So say P and Q are integers, are positive integers. Okay, and I define two equivalence relations possibly. A, x equivalent to y if x is congruent to y mod P and x congruent to y mod Q. Okay, so if only one, we know it's an equivalence relation. What if there are two, and we connect them by and? And then naturally, the second question is the second possible equivalence relation. What if we are combining these two congruences, but with the letter or? Okay, I hope you'll think about it. So is it clear what's being asked here? Well, I didn't ask anything. The question is, are these equivalence relations? So like 2 and 3, so divisible by 2 and divisible by 3. So two numbers are equivalent if under division by 2 and by 3 is the same. So for example, so 2 and 3. Let me have two equivalent numbers. So say 0, 6. 0 and 6. 0 is equivalent to 6, right? Okay, so it's divisible by, the remainder in the division by 2 is 0, and by division by 3 is also 0. So that's an example of an equivalence relation, of equivalence between two numbers. Whether it is an actual equivalence relation on the whole integers, that's for you to think about. Okay. Okay, so furthermore, with this, we will get to that back. I still wanna take a look and expand this equivalence relation, not this one, but rather congruency, and to numbers that are not necessarily integers. It's really not complicated, because if you think about this, as I said, this is all the integers, right? But between every integers, there are a bunch of real numbers. So I can think of this as actually a real line, and then what I'm doing, I'm wrapping the whole real line like this. Okay, so. Such as say, so I'm saying that my set will be not Z but rather R. Okay, and say X, well here's the X equivalent to Y if x minus y is an integer. So, for example, 1 is equivalent to 2, and to 3, and to 5, to 4. Okay? So all integers are equivalent, but also 1.5 is equivalent to 2.5, equivalent to 3.5, and so on. Okay, so the difference, as long as the difference is an integer, starting with 1, the two numbers are equivalent. Okay, so it's as if I'm wrapping really tightly so that there is only integer, every integer is going back straight to 0. 1 to 0, 2 to 0, 3 to 0, and they can't keep wrapping up. But as you can see, what we end up with is, so 0 is equal to 1. This is the number, and then all the integers or non-integers numbers are located on this circle. Okay, so that's another equivalence relation, which corresponds to something like, you can think about as a parametric curve of this circle. You can think of it as rotations, how past, say, 2 pi, you start repeating itself. So all of these are very important examples of equivalence relations. Okay, so what I want to do now is to turn to, so that we might talk about more about that, or you can think about it at home and convince yourself that this is indeed an equivalence relation. Is it? Well, let's go on with the axioms. We've had enough examples. Let's do something with the axioms, and so that is how actual mathematics works. You derive things directly from the definition without invoking anything else. And we, so far, that's all we have is our definition of an equivalence relation, and we want to derive certain things. But there is one more definition that we want to have here, and that is the equivalence class. So given a set X with an equivalence relation, sometimes, by the way, there might be more than one equivalence relation on the same set, as we already have seen. So suppose X is an X, then the equivalence class of X is the set of all y's in X equivalent to X. Okay, so that's a simple idea, right? So if we're talking about congruency, then every number that is divisible by have a remainder of under division by 3, say equal to 1, that's your equivalence class. So for example, if 1 is equivalent to 4, equivalent to 7, equivalent to 10, and so on, right? That's the equivalent. This is the equivalence class of 1. But it's also an equivalence class of 4, and of 7, and so on. Okay. What else? If it is equivalence relation is being a brother, then the set of brothers will be there will be like most of the people will have only, well, nobody. Well, we actually decided that brother is not an equivalence relation because you're not equivalent to yourself. So let's take some other examples of equivalence classes. So the trivial one, example 0. Number 2 is congruency already. Statements. So equivalence class is all the statements equivalent to a given statement. That is really might be hard to comprehend. What about that example of 2 parallel lines? So the equivalence class of every set is the set of all lines parallel to it. So imagine all the lines, there is a line, and all the lines parallel to it, they form its equivalence class. Okay? Similarly, somewhat, if you have a function, all functions with the same derivative form an equivalence class of that function. Okay, so no big deal. Just putting together all numbers that are equivalent to you to that particular element. So notation is in brackets. So x is an x, equivalence class is x in brackets. Okay? So the problem with this notation is that it is ambiguous. So a subset, well, let me make it clear, a set of all x's, so it is a subset of x to begin with, right? So we are not going anywhere away from x, so there are elements of x and there are subsets of x. So we have a bunch of subsets of x, possibly. Okay, so subsets of x. All equivalence classes are subset of x. However, representation, it specifies x in that notation. It is ambiguous because you can specify different ones. Just as the previous example shows that the equivalence class of 1 is the same as equivalence class of 4 or equivalence class of 7 and so on. So that's the ambiguity which we have to deal with. Okay, so if you have a brother, then all your brothers are the same as all his brothers. So you just put a label on it, and that is it is problematic because it will not tell you. You might have two differently labeled sets, and you won't know that they are the same until you actually examine it. Okay, so fortunately, there is this theorem which I've been mentioning, abstract theorem, based entirely on the axioms. So once again, x with an equivalence relation. We're looking at the intersections of equivalence classes. So there is an equivalence class of x, and there is an equivalence class of y. Well, there are only two possibilities. One is empty. Okay, so such as, well, there are two lines and they are not parallel. Their equivalence classes do not overlap, right? So that's the first possibility. What's the second possibility? They are equal, right? So either these two are x and y parallel. If they are not parallel, then there is nothing in common in the two classes. There is no somewhere element that they are parallel to both of them. Okay. And secondly, the second possibility, if they are x and y are parallel, then they belong to the same class. So that's the same class. The intersection of the two classes is the class itself. Okay. So the second possibility is x equal to y. So in other words, this is how we can put it: any two equivalence classes. Well, if two equivalence classes overlap, they are equal. Okay? So with parallel lines, the conclusion is predictable. With congruences, even are odd. If there are only two classes to begin with. And but the challenge of this theorem is actually not the examples. It's proving something that is kind of obvious. After you think about it, you take a few examples, of course, and then you say to yourself, of course it's obvious. So then the challenge becomes to actually proving it in the abstract. So what is the plan of the proof? You can think about it as if you have two cases, right? There are two cases, but actually you can simply do it by starting with, but pretty much by contradiction. So make a class that make a case that is show that one is the complement of the other. Okay, the two cases. Well, they are possible here. The point here is to demonstrate that there are no others, and two cases show they are complement. What does it mean? It means that if one is satisfied, then if one is not satisfied, then the other does. Okay? So specifically, we're going to start with, we will take the complement of the first. That's the easiest one. So either it's empty or it's not empty. So suppose, contrary to case 1, so this is case 1, case 2. So contrary to case 1, suppose that the intersection is non-empty.
It's what?
Non-empty. The intersection of the two equivalence classes is not empty. Okay, so let's expand. So what does it mean?
They're equivalent? They're equal?
No.
Contains all.
What?
Contains all real numbers?
No, first of all, there are no numbers. We're talking about sets in the most abstract, so the nature of sets is unspecified. So only set theory is available to us.
You said they overlap, right?
No, that is statement of the theorem. In that sentence over there is simply a restatement of the theorem. Let's make clear that it is you can see that sentence is the same as the theorem itself. So this is the formal statement of the theorem. This is its restatement, slightly more informal. So if two, and that's exactly that's the plan of my proof, as a matter of fact. If two equivalence classes overlap, they're equal. That's the plan. That's the plan of the proof. If the two sets, two equivalence classes overlap, they are equal. That's what I want to try to demonstrate. So suppose they overlap. That's what it means. The intersection is not empty. It means that there is an overlap. Okay, so, and I want to demonstrate that actually there is more to it, not just an overlap. They actually turns out to be equal. Okay, so that is the idea. But before I proceed, let's make sure that we see that it is exactly the same as the statement of the theorem itself. So they are equal. That the second line is they're equal, and the first line is the negation of our assumption. The assumption that I just made, suppose the intersection is non-empty, is the negation of what? Of what the intersection is empty, and that's case 1. So if you like, this is what this is: negation of case 1. Empty, non-empty. Okay, so that's negation of case 1, and now I would like to arrive to case 2. It will prove that they do overlap. They will prove that there are only two cases. Okay. Okay. So let's unwrap this. So this is the statement. So we have to put out of our heads what we're trying to prove, actually, and just what we know to be true, but rather work with only what we have available. So two equivalence classes, what does it mean for two sets? They're just two sets. They are, the intersection is non-empty. Non-empty means
Non-empty means?
yeah, what's the meaning of non-empty?
Something?
Contains an element, that's all. So it is this simple, yes. There is some element, say, A, that belongs to both of them, to the intersection to begin with, and then naturally, then we keep unwrapping it. What does it mean for an element to belong to the intersection of two sets? It means that it belongs to one and the other. Okay? A belongs to X, to the equivalence of X, and A belongs to equivalence class of Y. Okay? Any concerns? I'm not sure how well this is going so far.
There could be a value that doesn't belong to both, right?
Well, we don't know. Right, we make no assumption about that. Oh, we know that this is non-empty, which means there's an element there. Suppose let's call it A, and then it belongs to the intersection, means it belongs to both of them. Okay, so this is so far nothing but a set theory. Non-empty, what it means, and intersection, what it means. Finally, now we have to invoke the definition of the equivalence class, which is right above, right there. Okay, so we have two equivalence classes. Let's unwrap it. Equivalence class of all set of all x, y's element equivalent to x. Okay, so let's look at one at a time. A belongs to equivalence class of x. What does it mean? Well, take a look. What does it mean to belong to the equivalence class of x? Would it help if? No. Would it help if I put here A? Since we're talking about A. So x is given, okay, and then we have an equivalence class, the set of all a's equivalent to x, or A equivalent to x. That's the whole meaning. There's really nothing else going on. So the challenge really is abstraction here. But the good news is that everything is right there. So you don't have to search through this thick textbook to find some theorem or fact that you might need from elsewhere and you didn't think of it. This is the definition. The plus the three axioms of the equivalence relation is all we have. Okay, so we don't have to search for anything. We just have to have like 2 pages of text or less in front of us, and we'll have everything we need. We just have to think straight. Okay, so once again, A belongs to the equivalence class of X, has one and only one meaning. I guess that's wasn't quite clear. So let me write it out. Okay, so let me write it out. What equivalence class of X is? A is in X, A equivalent to X. That's all. This is the definition, right there. The equivalence class is simply the set of all elements equivalent to X, period. So then, based on this, as you can see, if A belongs to the equivalence class of X, it implies what? A equivalent to X, that's it. So that's where we are in our proof. We have A in X, and that means one and only one thing. A is equivalent to X. Okay? A equivalent to X. Okay, so far we are doing like equivalent substitutions, and so that's the meaning of that notation. We unwrapped it, and we have A is equivalent to X. Okay, and what? A is equivalent to 1. Yes. Okay. What do we do with this information? Based on the transitivity axiom, X is equivalent to Y. Okay, so x is equivalent to y, which means that what? X belongs to the equivalence of y, and y belongs to the um, equivalence class of x, right? So that certainly we can notice. So remember, so what we're supposed to prove is this. That's what we would like to demonstrate. So if x and y are equivalent, let's show that the sets are equal. The equivalence classes are equal. Okay, so let me write it without jumping to conclusions. So let's show now that the equivalence class of x is equal to the equivalence class of y. To showing that two sets are equal, that's, yeah?
Is X equivalence class equivalent to X?
No, we don't have equivalence between equivalence classes, only between elements. Even though you can probably think of, so feel free to think of a way how the equivalence relation creates an equivalence relation on the sets. I don't know. Well, anyway, so we know this one is equal. So this is equal. So we want to show that two sets, these are just sets, that they're equal. What does it mean? It means that one is subset of the other. So we show first that this. Okay? So in other words, once again, we remember what it means that, let's call it B. So B belongs to the equivalence of x. Supposed to imply that B belongs to the equivalence class of y. Once again, unwrapping, B is equivalent to x implies that B is equivalent to y. Because it's true, because, once again, transitivity axiom. Okay, so you can reverse this order in order to be really precise. So by the transitivity axioms, if B, I'm going backwards then, like this. So if B equivalent to x, then B is equivalent to y. Why? Because x and y are equivalent. Okay, and then furthermore, then it means that if B is in the equivalence class of x, then it is in the equivalence class of y, which means that the former is a subset of the latter, and then we reverse the things. And then same way, we show that the equivalence class of x contains the equivalence class of y in the exact same manner, and so the proof is then finished, right? So these two facts, number one and number two, give me this, and that finishes the proof. Not long, and you can actually distill it into even more precise and more compact proof. If you already know what the proof is, then your life is then it is sort of your responsibility to put the proof in such a way that it's easy to read, rather than the way we did it in kind of a discovery style proof, which sometimes turns into something that goes backward. So it's a practice that you should adopt. If once you discover the proof, you didn't know the proof in the beginning. Okay, so then once you discover the proof, write it up in a more precise way, so there would be no gaps. No gaps, or rather jumps to conclusion or reversal of the logic as I did. So that's just a practice that is a good idea to stick with. So as you can see, the proof fits into one little page. We use the transitivity axiom twice. Okay. We also use the the symmetry axiom. We used it implicitly. It's just not visible, but we freely replaced x equivalent to y, y equivalent to x. We did it a few times without actually thinking, which is fine. What does the reflexivity axiom tell us about the equivalence classes? Well, let's look. This is the definition of the equivalence class. You remember what the equivalence class is. So, reflexivity axiom, what does it imply about equivalence classes? Reflexivity axiom is the same as x is equivalent to x. So what does it mean? What can you say about the equivalence class of x? It might sound trivial once you say it. But we still should say it.
X is equal to X.
No, it's not equal to x, no. What can you say about the equivalence class of x?
Contains all elements of x.
It's a subset of X?
They're all subsets of x. So what was that?
Contains all elements of x.
Oh, x. Lowercase x? Lowercase x is just one element.
So lowercase x contains all elements of big X.
No. Well, it's actually, okay, where is it on? The answer is it contains x. That's all. X is equivalent to itself, which means that it belongs to its own equivalence class. That's all. There is really nothing else here. Like I said, it's trivial, but it has to be spoken. Okay, I'll see you tomorrow.